set? We're all set?
Yeah, I think we're all set.
Okay, so the next talk will be given by Arthur and Iona on almost fair simulations.
Yeah, so we are indeed going to be talking about almost fair simulations, and this is joint work with our PhD supervisor, Bernd Finkbeiner. So what is this talk about? In this talk, we're going to be focusing on proving language inclusion between non-deterministic Büchi automata. And if you do not know what a Büchi automata is, it's simply like a standard finite word automata, except that we are going to run them against infinite words, so infinite sequence of letters. And the semantics is that an infinite word is accepted if a final state is visited infinitely many times. So now you might wonder, why would we bother? And the reason why it matters is that many challenging problems can be modeled in terms of language inclusion between two non-deterministic Büchi automata. And a particularly interesting instance of that is the case of verification of temporal properties under fairness assumptions, and in particular liveness properties under fairness assumptions. Okay, so as a motivating example, we're considering a little concurrent program. It's concurrently executing two loops, one that prints A's and one that prints B's. And the specification that we would like to prove is that globally, eventually A or A is printed infinitely many times. And if we want to prove that, we'll need to assume that the scheduler is fair. And in particular, we need to make the assumption that the left thread is never starved. And we can model this whole situation using two Büchi automata, one that is essentially encoding the program plus the fairness assumption, and one that is encoding the specification, the liveness specification. And it turns out that the program satisfies the spec if and only if those two automata are language included. And the key takeaway here is that on the left-hand side, we're going to model the fairness assumption as accepting states. So here the Q1 models the fact that the left thread is never stuffed. And on the right-hand side, on the specification side, accepting state are modeling liveness objectives. So here the R1 state models the fact that we're seeing an A. All right. So now the big question is, how do we actually verify language inclusion? So there exist many algorithmic approaches to do that. For example, there are decision procedures based on automata complementation. But first of all, those are computationally very expensive, and they're essentially restricted to finite state automata. There also exists an alternative option, which are incomplete algorithms based on a notion of fairness-preserving simulation. This is computationally much cheaper, but it's still restricted to finite state, or at least in the literature, it's mostly been studied in the context of algorithmic analysis of finite state systems. And now the question we are asking in the context of this talk is, beyond algorithmic methods that are essentially restricted to finite state, can we also do interactive deductive proofs and exploit this as a foundation to do potentially infinite state systems? To bridge this gap, we're presenting a family of deductive systems to prove language inclusion of NBA, which is based on both known and novel fair simulation techniques. But the key idea here is that those deductive systems are going to support a very intuitive style of incremental proofs via parameterized co-induction. And because we are in a deductive and interactive setting, the cardinality of the state space doesn't matter. So we can support finite and infinite state automata. The cardinality really is not playing a role here. And the whole work has been mechanized in ROC, which both means that we are giving formal foundations. We rigorously argue about the soundness of our fair simulation techniques. And on top of that, because it's mechanized in ROC, we can use our deductive system with the help of the proof assistant.
A little bit about how we prove this language inclusion by fair simulations. And before we do that, microphone. Before we do that, I will just talk about what is a simulation formally. So let's imagine we are given two Büchi automata, and we want to prove that two states are similar, or they are in the simulation. And we know that with this smaller equal, so we want to prove that or show that these two are similar. And the definition is exactly that for all outgoing transitions from the left state, we need to find a matching transition for the right state, such that the target states are then again in our simulation. So basically, the executions from S1 are mimicked by the execution from S2, so we're just checking that like the traces are the same. So if you remember the definition of Büchi automata, there was this acceptance condition, and this very plain definition of simulation does not talk about this acceptance condition at all. So this particularly means that the fair executions from S1 are not guaranteed to be also simulated by fair executions from S2. And there's one basic idea to fix that, and it's called direct simulation. And this is by updating our definition a little bit. So we added a condition here which states that if we are in an accepting state on the left, so in S1, then we also need to be in an accepting state on the right, so S2, which basically means that we need to sync up the existing states, and so therefore we enforce that all fair execution from S1 are also simulated by fair executions from S2. And this still gives us a soundness theorem, so if we can show that they're simulated, then they're language included. Okay, and before I will talk about further simulation.
All right. So Iona explained the trick of direct simulation to get a first soundproof technique for language inclusion. But how do we actually use it in practice in the proof assistant? And what we're going to do is that we're going to package a direct simulation in a little deductive system by manipulating triple with a guarded context. And the idea is that on the right, we have the two states we need to prove to be similar or directly similar. And on the left-hand side, we have a so-called guarded context that contains pairs of states. And the intuition here is that a triple holds means that S1 is directly similar to S2 under the guarded assumption that everything in the context is already directly similar. So before I explain what this guarded thing means and how we are actually operating those triples, we can already claim soundness. So if you can prove such a triple starting from an empty context, you have language inclusion. And the way those contexts are working is as follows. So first of all, to take things out of the context, whenever the box around the context is open, you can always conclude a proof if the states you're looking at are already in the context. So this is how you take things outside of the context and how you conclude a proof. And now the question is, how do we get things inside of the context? And the idea is that whenever you want, you can always accumulate the current states that you're looking at inside of your context. But very importantly, this preserves the guard around the context. And last, whenever the context is open, you can always decide to close it, so it never hurts to close it. So that's all about opening the context, or using what's inside of the context, adding stuff in the context, and closing the context, but the big question is, how do you actually open the context? And to do so, there is essentially two ways to make progress. The first one is, so long as the S1 state is not accepting, you can always take a step and open the guard. And another way to make progress is to exploit the fact that the current state you're looking at is accepting in the right. And in that case, you can also take a step and open the context. So let's look at a concrete example. So we take 2 times exactly the same automaton. It's accepting the word AB, 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 AB. We start in Q0 or 0. And the first thing we're going to do is accumulate the initial state in our context. Then we're going to take a computation step. And because we are now in a pair where R1 is accepting, we can use the final rule and go back to Q0, R0. And this time the guard is open. And because Q0, R0 is already in the context, we are done by cycle. So very simple intuition.
Okay, so back to our direct simulation. So unfortunately, direct simulation is still a little bit too strong. So if we take these two automata in our example, it's almost the same, but we change the accepting state here from R0 to R1. So there is still language included because both automata still only accept the word AB, 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 but actually Q0 and R0 are not directly simulated anymore because the accepting states doesn't match up exactly. A way to circumvent that is so-called delay simulation. So delay simulation has this intuitive idea that we delay the time we need to see the second accepting state. So after we see an accepting state on the left, so F1 accepting state, we can finally delay, so do finally many steps until we see a subsequent listen to an accepting state on the right. And even with this more weaker notion, this is the sound for language inclusion. Let's now look at how this would look in our deductive system. So this general idea, so we see an accepting state on the left, and then we need to check finally many step until we are allowed, until we see a final state on the right. We do this with 2 kinds of triples, so we have our left triple and our right triples. And the idea is now exactly that. So we have the left triples where we start, and we stay in there until we see a final state. Then we notice that we see a final state on the left, and then we switch over to the right relation where we then stay in step until we see a visit to an accepting state on the right. So we wait there, and then we go back to the left relation, and it starts again. So they play like together. Okay, and with this, we again get soundness. So if these two states are simulated, then there are also language included. Okay, how does this look exactly? So let's look at the rules. So we first look at the left rules. So when we search for an accepting state on the left, so we still have the same rule, which says as long as we do not see an accepting state, we can just go on and open the context. And then we have the other rule that if we then see an accepting state, we need to switch from the left relation to the right relation. And then we have the right rules. So first, as long as we don't see an accepting state, we can just step. But importantly here, the context stays closed, because this is just like a helping thing where we track finitely many delays. And then this is the rule that helps us then to open the box again. So if we see then a finite state on the right, then we can step and open the context and also get back to the left relation here from the right. Okay, let's look at an example. So I took the example from before. So these are our accepting states. And we start from Q0 and R0, and we start in the left relation. So first, we want to accumulate these states. So remember that you've already seen them. Then, because Q0 is accepting, we need to track that and need to switch to the right relation, and therefore switch to the right relation, but this is not final, R0 is not final, so we do a step. So we switch to the right relation and then do a step, as R0 was not final. And then afterwards we are in Q1 and R1 is now final, so we can use our final rule to then step again and open the context, and then we are back at Q0, R0, and these we all have already seen, so we can conclude with our cycle rule. Okay, unfortunately, delay simulation is still too strong, so if you look at the following example, both automata just accept the empty language because they just loop indefinitely at a non-accepting state. But the left automaton has some random accepting state in the beginning. And therefore, Q0 and R0 are not delay simulated anymore, because this accepting state here forces us to go into the right relation, but then we never see an accepting state here, so we kind of are stuck in there.
So this example seems a little bit artificial, because actually the languages are empty, so we could as well have removed the accepting state here. But it turns out that this is not always the case. So this problem can actually occur in practice on non-trivial Bucci automata. So for example, here we have an example where we have some sort of a scheduled task where we start in some state Q0, then we might schedule a task, then there is an initialization phase, we work for some amount of time, and then at some point we are done, and we have a fairness condition that guarantees that we are doing this infinitely many times. And the specification that we care about is to show that we terminate the task at least once. And it turns out that actually we can also not prove this by delay simulation, and the reason is simply that once we are getting to Q1, this generates an obligation to have a visit to R1, but the left-hand automaton can stay stuck in Q2 forever doing some work, and we have no way to get out of that. So to weaken delay simulation, we propose a repeated delay simulation. And the idea is that we still enable delay, like in delay simulation, but we additionally enable to skip finitely many visits to F1. So we're going to generate less obligations to visit F2 states. So this is still sound for language inclusion. The way we're going to implement a deductive system for this is by adding a new kind of triple. So we still have the left and right triples that are inherited from delay simulation, but on top of that, we also have a new kind of weighting triples. And the intuition is still the same for the left triples. We are tracking visits to F1. Upon visits to F1, we are forced to switch to the right relation, which forces us to eventually get to an F2 state. But this time, instead of circling back to L, we are actually going to those weighting triples, which enable to first skip finitely many visits to F1 before we commit again to tracking F1 states. So this is still sound for language inclusion, and in particular, we get to start from a weighting triple, so we can wait in the beginning as well. All right, so how does it look like? We need to update slightly our right rules. So we still have the delay rule. So we preserve the ability to delay as in delay simulation. But the twist is that now whenever we see an F2 state, instead of immediately going to L, we can go to W and wait for some time. So skip some obligations temporarily. And so the waiting rule are as follow. We can always unconditionally take a step so long as we're in wait. But in addition, whenever we want, we can actually open the context, so long as we commit to start tracking F1 states again. So to see how it works in practice, let's look at this example that we discussed before. So we start in Q0, R0. And the key idea here is that we are going to wait to skip through the Q1 state and not generate an obligation. So we use the rule wait 2 times, and we get to Q2. But very importantly, the visit to Q1 did not generate any obligation. And then from this point on, we can use accumulate to store Q2 and R0 in the context, and the rest of the proof is essentially straightforward. So I'm not going to give the full technical details. All right, so as a summary, we started from a direct simulation and presented a deductive system associated with it and proved that it's sound for a language inclusion. We also discussed that direct simulation is way too strong in practice, and we discussed how delay simulation is much weaker and can still be presented as a very intuitive deductive system. And finally, we presented an even weaker and new notion of fairness-preserving simulation called repeated delay simulation, and it still preserved this nice deductive system. So all the results and all the deductive systems have been mechanized in ROC, so feel free to have a look at the ROC development online. And as a conclusion, maybe a few words on potential future work. So even though the repeated delay simulation is significantly weaker than delay and direct simulation, it's still too strong. There are examples that are not covered. But there exist in the literature some weaker notions of fairness-preserving simulation. Unfortunately, those require some very sophisticated co-inductive, inductive, co-inductive reasoning. So there is a lot of work to be done here, but it's not obvious that we can still have those nice deductive systems to reason about them. Another line of work would be to look at other fairness conditions than Bucci. So in the context of this talk, we talked about Bucci automata, but actually there are other kind of infinite words automata with slightly different acceptance conditions. It would be very interesting to look at fairness-preserving simulation for those as well. And last, in this talk, the deductive system we looked at are very low level. We reason directly against models of programs and explicit states. It would be much nicer to combine this with a program logic, for example, in a style of similaris. Yeah. So that's it. If you have questions, we are happy to answer them.
Okay, any questions? Maybe I start then. So, I mean, there are very fancy forms of simulations like up-to, right? Can you reflect this in your system, up-to techniques?
Yeah, that's a very good question. Yes, it's possible, but there are things you need to be a little bit careful about because, so one thing that I've been thinking about recently is whether this supports up-to context. And I think it kind of depends. Because if your context introduce some new some new obligations, so some new F1 states, then it's not clear that you can reason up to context. So I think you need to be a little bit careful, but there are other up to techniques that should work. But yeah, this is a very good, good remark. Short answer is probably, but I need to investigate more.
Right. And maybe on a related note, so personally, before I learned about fair simulations, I learned about Ramsey-based inclusion checking techniques for Bucci automata. Do you know if this is somehow related to the simulation-based stuff, and whether you can reflect this also in a proof system? That would be quite cool.
Do you know? Yeah. No, I have no idea. Honestly.
Yeah, yeah. I think it goes back to Clemente and people like this, but yeah, okay, it would be quite interesting to see it. Okay, any more questions? Yeah.
Hi, thanks for the talk. I feel like I got from the summary a pretty clear idea of why you can't just rely on your standard old simulation techniques. I don't have as good an idea of intuitively how I should understand the context being open or closed. I was wondering if you might be able to patch that in.
Yes. So the opening and closing the context is just this idea of parameterized co-induction. It's actually not from us. It's a standard idea now in the field of interactive proofs by co-induction. It's just here to model the fact that actually we had a talk about co-induction earlier that was mentioning this difficulty of context, of guards. Like you need to have your when you're using a co-induction hypothesis, you need to make sure that it's guarded. And this is exactly what this corresponds to the idea that you cannot directly use your co-induction hypothesis before you actually made some progress. So the guard around the connex is just here to make sure that you are actually making some progress towards your goal before you're exploiting the co-induction hypothesis.
Should I understand as sort of like a dual of a termination check almost, or? Okay. Anyway, sorry, I wasn't here earlier.
I'm not so sure about that. It's more like it's one way to understand this guardedness condition in standard co-inductive proofs.
Okay, thanks.
Any more questions? If not, then thanks to both of you again.